Greetings, galactic enthusiasts, and welcome once again to another fact-driven documentary about space science and exploration. Have you ever wondered what secrets an interstellar traveler might carry across the vast darkness between stars? Right now, at this very moment, something extraordinary is unfolding in our cosmic neighborhood. A visitor from another star system is racing through our solar system. And what happened just weeks ago has astronomers questioning everything they thought they understood about objects from beyond. Therefore, stay tuned, because what I will explain will expand your knowledge about interstellar objects. And if you're fascinated by the mystery of 3I Atlas and want to see more amazing cosmic stories, hit that like button and let the cosmos know you're watching it. Every click helps keep the search for the unknown going. Comment below and let me know from where you're watching this. I'd love to read from what corners of the world you are witnessing this with me. Picture this. Late November, telescopes around the world locked onto a single target. Astrophotographers in Spain, United States, Chile, and many other remote fields across the globe, all capturing images of the same mysterious wanderer. And when those images came through, what they revealed stopped the scientific community in its tracks. Comet 3I Atlas, the third confirmed interstellar object ever discovered by humanity, had transformed. A massive tail now stretched behind it, 5 million miles of glowing gas and dust, trailing through space like the wake of a cosmic ship. But that wasn't the strangest part. Not by a long shot. Extending in the opposite direction, pointing directly toward the sun, was something that shouldn't exist. An anti-tail. Over 1 million miles of material, pushing against one of the most powerful forces in our solar system. To understand just how bizarre this is, you need to grasp what's happening up there. The sun doesn't just give us light and warmth. It continuously blasts our solar system with a stream of charged particles, the solar wind, racing outward at 400 kilometers per second. That's over 890,000 miles per hour. This invisible torrent shapes everything it touches. It's why comet tails always point away from the sun, blown back like cosmic windsocks. It's the rule, carved in physics, observed in every comet we've ever studied, until now. For 3I Atlas to push material over 1 million kilometers sunward, battling directly against the solar hurricane, the physics involved defy easy explanation. Scientists calculated the ram pressure required, and the numbers are staggering. To penetrate that far into the solar wind demands mass densities 1 million times greater than the background solar wind itself. This isn't gentle outgassing, the kind we see from typical comets. This is explosive mass ejection, on a scale rarely witnessed. What could drive such violence? If this is natural, if sunlight is simply warming volatile ices that then explosively sublimate, then the composition must be extraordinarily exotic. We're potentially looking at materials that exist in abundance around other stars, but are vanishingly rare in our own solar system. Think about that for a moment. 3I Atlas might be carrying chemistry from another stellar neighborhood, substances forged in different stellar furnaces, cooled in different conditions, representing 4.5 billion years of evolution in an alien environment. And there's more. The tail didn't just appear overnight. When scientists first detected activity from 3I Atlas back on July 2nd, just days after its discovery on July 1st, 2025, they observed something peculiar. Instead of a typical comet tail, they saw focused jets. 7 distinct streams of gas blasting into space, some pointing away from the sun, but several shooting directly toward it. These weren't diffuse, fuzzy plumes. They were tightly collimated, structured, powerful enough to maintain their distinct forms even as the comet spun once every 16 hours. But within 24 hours, everything changed. Those 7 jets merged into one massive plume, that near 3 million kilometer structure that would grow to 5 million miles over the following months. It was as if the comet had suddenly shifted gears, transitioning from controlled bursts to sustained violent activity. Here's where this story gets deeply interesting, where the questions scientists are asking become profound. Most comets are irregular chunks, tumbling unpredictably as they orbit the sun. This random rotation causes their jets to spray in different directions, creating a stuttering, variable brightness pattern as different surfaces heat and cool. But 3I Atlas, its activity shows consistency. Those jets maintain their structure. The brightness increases steadily. There's an organization to the behavior that suggests something more than random sputtering. Could this simply be a comet with unusually uniform composition? Perhaps. When ice sublimating from the surface is heated evenly, you might see steady output. But there's another detail that complicates this picture: the non-gravitational acceleration. This isn't just about tails and jets anymore. Measurements now confirm to 10 standard deviations, meaning this is real, not measurement error, show that something is actively changing 3I Atlas's path through space. For a natural comet, this acceleration requires massive jets of gas and dust shooting out asymmetrically, acting like tiny rocket engines. And the calculations suggest 3I Atlas is losing billions of tons of material. Current estimates indicate it might shed possibly over 10% of its total mass in just 2 months. Let that sink in. If you started with a mountain, and in 60 days it lost 10% of its mass through explosive venting, you'd be witnessing something extraordinary. That's what's happening out there, right now. But here's the puzzle. The amount of mass loss needed to produce the observed acceleration doesn't quite match the traditional models. Some researchers have quietly noted that if hypothetically this were something other than a completely natural comet, if there were any technological component, far less mass would be required to achieve the same effect. Chemical or ion thrusters could produce the observed acceleration while expelling significantly less material. Now, before we go further, let's be absolutely clear about something. The overwhelming majority of astronomers believe there are natural explanations for everything we're observing. They argue that our models of interstellar objects are based on a sample size of just 3 confirmed visitors: Oumuamua, 2I Borisov, and now 3I Atlas. That's far too small to establish what's normal and what's anomalous for objects from beyond our solar system. Every new interstellar visitor teaches us that the universe is more diverse, stranger, more wonderful than we imagined. But the accumulating questions demand attention. Why is 3I Atlas so much brighter than models predicted? Research from the Lowell Observatory and the U.S. Naval Research Laboratory quantified this anomaly. They found the comet's brightness increasing inversely proportional to its distance from the sun raised to the power of 7.5. To put that in perspective, comets from our own Oort cloud typically show an exponent between 2 and 4. 3I Atlas is nearly doubling that rate. That's not a small discrepancy. That's a fundamental difference requiring explanation. What could cause such extreme brightening? One hypothesis involves supervolatile ices, materials that vaporize at much lower temperatures than water ice. We're talking about frozen nitrogen, carbon monoxide, carbon dioxide in abundance, compounds that might be common in the frigid depths of interstellar space, but are rare in solar system comets. James Webb Space Telescope observations confirm this. The comet's coma is dominated by carbon dioxide, with substantial amounts of water, carbon monoxide, and other compounds. As 3I Atlas approaches the Sun, these materials could be boiling off explosively, creating the brilliant coma and those extensive tails we're seeing. But there's another pattern that intrigues researchers: the trajectory. According to new calculations, 3I Atlas isn't just passing through our solar system randomly. On March 16, 2026, it will reach Jupiter's Hill sphere, the region where the giant planet's gravity becomes dominant over the Sun's. This gravitational encounter could fundamentally alter the comet's exit path from our solar system. And here's what's remarkable. Some scientists have calculated that the approach to Jupiter's Hill radius can be predicted to be better than 4 significant digits. Think about what that implies. An object that traveled through interstellar space for potentially millions of years, experiencing countless gravitational perturbations from passing stars, dust clouds, and cosmic debris, somehow arrives at our solar system with a trajectory precise enough to target Jupiter's gravitational sphere of influence with extraordinary accuracy. Is that coincidence? Statistical fluke? Or is there something about interstellar objects we fundamentally don't understand? NASA's Juno spacecraft, currently orbiting Jupiter, might have an ideal observation window sometime around March 2026. Imagine that. A probe designed to study Jupiter, potentially getting a front row seat to witness an interstellar visitor's gravitational dance with the largest planet in our solar system. If Juno can observe 3I Atlas during this encounter, scientists might measure its response to Jupiter's gravity with unprecedented precision. Any anomalies in how it responds, any unexpected course corrections, could provide crucial data about its internal structure, mass distribution, and composition. But we're not waiting until March. The closest approach to Earth is coming much sooner. On December 19th, 2025, just weeks from now, 3I Atlas will pass within 269 million kilometers of our planet. In cosmic terms, that's relatively close. Close enough for our most powerful telescopes to capture detailed observations. Right now, observatories around the world are preparing for this opportunity. The Hubble Space Telescope and James Webb Space Telescope are both being positioned. Ground-based telescopes in Hawaii, Chile, and Spain are coordinating their observation schedules. These aren't just pretty pictures scientists are after. They're planning comprehensive spectroscopic analysis to identify the exact chemical composition of those jets. They want to measure the precise speed of the material being expelled. Natural sublimation of ice by sunlight produces gas moving at predictable speeds, typically a few hundred meters per second. By measuring the velocity of material in those jets, scientists can begin to narrow down the mechanisms at work. Is this water ice, carbon dioxide ice? Something more exotic? The December data will tell us. There's also the matter of the nucleus itself. Despite all these observations, we still haven't gotten a clear look at the solid body at the center of all this activity. The brilliant coma obscures our view of what lies beneath. The December flyby might change that. With Earth at closest approach, our most advanced telescopes should be able to peer through the glowing envelope and possibly image the nucleus directly. Will we see a rough, irregular chunk of ice and rock like other comets? Or something with unexpected features? The resolution might not answer every question, but any data about the nucleus's shape, size, and reflectivity will help solve this puzzle. The timing of all this is remarkable. 3I Atlas was discovered on July 1st, 2025, giving astronomers just months to prepare for its closest approach. Compare that to the years we typically have to plan observations of known comets returning to the inner solar system. This compressed timeline has forced unprecedented coordination. Observatories across the globe have been sharing data in real time. Amateur astronomers with backyard telescopes have contributed crucial observations that helped refine the object's orbit. Space agencies have reprioritized telescope time. Even Mars-orbiting spacecraft, like the European Space Agency's Trace Gas Orbiter, have contributed data, using their unique vantage point to refine trajectory calculations. All of this collectively is a reminder that in the search for answers about our cosmic neighborhood, every observer matters. Every data point contributes to the larger picture. This is science at its finest. Humanity reaching out to touch the unknown, asking questions previous generations couldn't have imagined, building knowledge one observation at a time. And beyond the immediate scientific value, something profound is happening. We're routinely detecting objects from other star systems now. These aren't just rocks and ice. They're physical connections to places light years away. Every atom in 3I Atlas was forged in another stellar system, orbited another sun, and experienced conditions we can only imagine. When we analyze this object's composition, we're literally examining a piece of another world. The isotope ratios, the molecular structures, the physical properties. All of this carries information about the environment where 3I Atlas formed. Was it a young, hot star rich in heavy elements? An old, cool star with different chemistry? A binary system with complex gravitational dynamics? If we can characterize enough interstellar objects, we can start to map the chemical diversity of the Milky Way. We can identify patterns, figure out which stellar neighborhoods produce certain types of objects, and ultimately better understand the processes that create planetary systems like our own. But here's something that keeps astronomers awake at night. How many of these objects are out there right now, passing through our solar system undetected? Our ability to spot interstellar visitors has improved dramatically in recent years, thanks to automated sky surveys and better detection algorithms. But we're still only seeing the brightest, most active objects. For every 3I Atlas we detect, there could be dozens or hundreds of darker, quieter interstellar objects slipping through our neighborhood unnoticed. Some might be inactive comets with no outgassing to make them bright. Others might be rocky asteroids that barely reflect any light. That's why each detection matters so much. Every interstellar object we study helps us refine our detection methods, understand what signatures to look for, and ultimately spot more of these visitors. It's a feedback loop where each discovery makes the next one more likely. And with each new visitor, we're learning that the universe is more diverse, stranger, and more interconnected than we ever imagined. The story of 3I Atlas is still being written. As you listen to this, the comet is racing toward its December rendezvous with Earth's telescopes. What will those observations reveal? Will we confirm that 3I Atlas is an exotic but natural comet with unusual composition forged around another star? Will we find evidence of processes that challenge our current models? Or will we discover something so unexpected that it forces us to completely rethink what we know about interstellar objects? The honest answer is, we don't know. And that's what makes this moment so extraordinary. This is real exploration, real discovery happening right now. We're not looking at distant galaxies or ancient light from the early universe. This is an object in our cosmic backyard, close enough to study in detail, strange enough to challenge our assumptions, mysterious enough to inspire wonder. Whatever we learn in the coming weeks will be discussed for years, probably decades. This is the kind of event that defines careers, inspires new generations of scientists, and expands humanity's understanding of the universe we inhabit. For young people considering careers in astronomy, planetary science, or engineering, moments like this reveal the frontier that awaits. There are mysteries up there demanding solutions, puzzles requiring the next generation's brilliance and creativity. The tools being used to study 3I Atlas, the James Webb Space Telescope, advanced spectroscopy, sophisticated orbital mechanics. These weren't available even 20 years ago. Imagine what instruments and techniques will be available in another 20 years in your careers, in your hands. For those who've watched the space program evolve over decades, who remember when interstellar objects were purely theoretical, this is validation. The universe is even stranger and more wonderful than we hoped, and we're finally developing the technology to study it in detail. 3I Atlas is more than a comet. It's an ambassador from another world, a cosmic messenger carrying secrets about stellar systems we can never visit, but desperately want to understand. Every measurement we take is a conversation across the light years. Every spectrum we capture is a letter written in the universal language of physics. And in those spectra, those measurements, those carefully analyzed observations, we're reading messages about the nature of our galaxy, the diversity of cosmic environments, and our place in this vast, interconnected universe. The 5 million mile tail, stretching behind 3I Atlas, isn't just ice and gas scattering sunlight. It's a flag, planted by nature itself, saying, "Look here, pay attention. There are wonders you haven't imagined." And that sunward anti-tail, that defiant plume pushing against the solar wind, is a challenge. "Explain me," it says. "Understand me. I don't fit your models, your expectations, your comfortable assumptions. I am something new." And so, in observatories around the world, scientists are rising to that challenge. They're pointing their instruments skyward, capturing photons that traveled across the galaxy, only to end their journey on our detectors. They're running simulations, testing hypotheses, preparing for the December observations that could finally provide answers. Or, perhaps more likely, provide even better questions. Because that's how science advances. Not through comfortable certainty, but through curiosity, sparked by mystery. Not through having all the answers, but through asking better questions. 3. Atlas has given us extraordinary questions. In a few weeks, we'll begin gathering the data to explore them. And whatever we discover will open new chapters in our understanding of the cosmos. This is our moment. This is our chance to witness something that happens perhaps once in a generation. An interstellar visitor, close enough to study, strange enough to challenge us, timed perfectly for our best instruments to observe. The December observations are coming. The data will flow, and humanity will add another chapter to its growing understanding of the universe beyond our sun. If you're fascinated by the mystery of 3i Atlas and want to see more amazing cosmic stories, hit that subscribe button and let the cosmos know you're watching it. Every click helps keep the research for the unknown going. Comment below and let me know where you're from. I'd love to see what corners of the world are witnessing this with me. Keep looking up. The cosmos is full of wonders. And right now, one of the most intriguing things we've encountered in years is speeding through our solar system, carrying secrets from another world, challenging us to understand, to question, to explore. This is the Infinite Voyage, providing educational entertainment, not just of objects through space, but of human curiosity through the cosmos of the unknown. And you're witnessing it unfold in real time, right now. Thank you for watching, and until next, keep searching within.